All right, great. So hi, everybody. Welcome to the second lecture of CS25 this quarter. And so today we're very lucky to have two speakers here with us. So Hazel, or Hyojung Nam, is here in person today. She's a master's student at Brown University working on representation learning, causality, and self-supervised learning. And we also have Lucas Maes over Zoom, who will be speaking afterwards. And he's a PhD student at Mila and the University of Montreal working on JEPA and planning. So I'm sure they're going to give us a very insightful talk today. And so without further ado, I'll hand it off to Hazel.
Yeah, thank you for introducing Hazel, first-year master's student in Brown University working with Professor Rendell Bolas-Rio. Our lab is working on JEPA, self-supervised learning, and some theory as well. Today, I'm a bit nervous. This is like first time giving a talk in English, but at the same time, I'm really, really excited to talk about JEPA word model and my recent work, Causal word model. I'm pretty sure Lucas is also very excited to share his very recent work, LeWorldModel. Okay, so the first part of this talk will be about the concepts of JEPA and word model. And after a brief introduction of those two concepts, we will talk about the Causal JEPA paper first, which gives a question about how to make a model understand the object interaction. And then I will hand over to Lucas, and he will talk about LeWorldModel. And LeWorldModel is about the end-to-end JEPA training without collapse. So first of all, I think most of you guys may heard of word model, and some of you guys may be really be familiar with. What is the word model? To talk about the word model, we should have this first. So this is autoregressive model, right? You get the previous state and you predict the next step. However, this is sometimes not enough to describe the world. Why? Because our world have uncertainty. At the time that you're observing, someone might do something at that time, right? Someone can throw something. There's like inherent uncertainty. To handle this, you need an action. And this now is a word model. So the word model basically is a function that gets the previous state and the action to predict the next state. And in this sense, I perceive the word model terminology as a simulator. So as an AI researcher, what would you do to make this word model better? In my opinion, I think three points of designing. The first one is having a good state representation. This is about, so you probably are not going to give the raw pixel images or like raw pixel values to the predictor. You somehow have to have a good representation that reflects the world faithfully. And the second component will be good transition model. For example, there should be a grounding rule like underlying the environment. For example, there's a gravity that exists. We have to understand these rules to predict the world and, to simulate the world. And the last component is the good dynamics model. Now you're going to do some action. And your model should react to your action in an appropriate way. Keep these three things in mind because I'll revisit this end of this, the Causal JEPA part to discuss like how I address these three questions. Today we will not cover generative word models. There's like so many industries now like are doing the word modeling stuff. For example, Gaia is an autonomous driving model that gets the action in the previous state to predict the next driving scenario. And the Genie, they want to scaling up the word model, so they learned there's something called latent action, which is a proxy of the action. Because usually online data doesn't have the per frame action annotation. And Sora is like a technically video generation model, but their fidelity of their generated scene is very good, so they got a lot of notice. And Marble from Professor Fei-Fei Li in Stanford, they are doing the 3D interactive environment so that we can interact or explore. But today we will talk about joint embedding predictive architecture, which is somewhat different from the generative word model. So on the left side, the thing you see is generative word model, because as you can see, the X is the current state, and let's say the Y is the thing that we have to predict, which is like a future step. you put the encoded current state to the predictor, and you directly compare to y, which means that your model should give the same pixel space as your target is. However, in the right side, that is a joint predictive architecture. You see like both x and y are going to the encoder. So now we are comparing our prediction and the true target in the latent space. So why does it matter? We don't have decoder in the JEPA architecture, but it is not merely about having no decoder. It is about uncertainty in the world. So when human is thinking about like what is going to happen next, are you predicting something in the like a very pixel level? There's like some kind of uncertainty that you cannot predict, and there's obviously like your area of interest. So JEPA tries to deal with only having predictive information in your latent space so that your prediction is getting more meaningful and human-like way. And also, the framework can be interpreted in a different way. First of all, the generative world modeling is about like a likelihood. They learn the normalized likelihood over the future frames, but JEPA can be understood as an energy-based model. So in the very original paper that Yanlu Kun suggested, he framed the JEPA as an energy-based model. An energy-based model learns the energy score function that gives the high value if two value x and y are incompatible, and they give low score if those are compatible. And compatibility in the world model makes the point of the y is a plausible future of x. So the energy-based model can collapse, unfortunately. And there's two ways to prevent this collapse. The first way is contrastive learning, and the second way is regularization-based method. I'm not going to talk about this too deeply, but the regularization-based method are making very rich and well-defined energy landscape. So that is what JEPA is doing. For example, VJEPA, which is video JEPA, they took on input as the consecutive frames with the spatiotemporal masking. And they put this encoder, and they get the representation, and they try to predict what is happening in the unseen area. So the target has like every information. And here there's like some regularization tool to prevent collapse. For example, they use EMA encoder. EMA here means exponential moving average. This prevents like a really trivial collapses. And also you do stop gradient for the target encoder, and you put the mask to give a model more challenging task. VJEPA 2 is basically the same architecture as VJEPA 1, but they wanted to scale up. And they also did some interesting post-training. And one of them is action condition control. So now this became more like world model, because now it's getting, as you can see in the predictor, it gets the robot action and poses. So this is one of the post-training in the VJEPA 2. And this is actually called Dyna World Model and have a very same architecture as the action condition post-training that you just saw. So what the Dyna World Model is doing is they use the frozen Dyna V2 encoder. What they claim is, do we actually have to train the JEPA encoder to get the meaningful abstraction for planning? They said no, like a pre-trained Dyna encoder can do that role as well. So they generate patch representation, and with the auxiliary variable, for example, action and proprioceptive signals, they predict the future state representation, and they compare. And this predictor is just like a simple causal transformer, which predicts the future autoregressively. But here I want you to think about, is this the patch representation is what really humans do? Like, are we patchifying the image to, predict the next step? Probably not. So today we're going to talk about Causal JEPA, learning world models through object-centric latent intervention. Before starting this talk, I would like to thank you for my collaborators, Quentin, Lucas, and Yanukun and Randall Ballestrio. So the goal of the Causal JEPA is understanding the object interaction and object dynamics. These are 3 data sets that I picked to show today. The first one is push-T, pretty famous example in the control experiments. The goal is you do action on the blue ball, and you want to move the gray T block to perfectly overlap on the green T. And the second data set is clever. This is actually the video paired with question answering the data set. The question is like, it can be predictory, for example, what would happen in the next frame, and it can be counterfactual, for example, what would happen if the blue color cylinder doesn't exist. And it can be explanatory, so it's like basically VQA benchmark. And the third one is fear. As you can see, many objects are interacting each other with the grounding rule. For example, there's a gravity, the mass matters here, and etc. So to understand this object dynamics, what the current models are doing is like this. They patchify the image, and they try to predict what will happen in each patches. But what are you going to do to understand this mechanism is, you want to understand the things like this. You have each object, and you want to know like how one object influences each other. So what if, in the Dyna-War model, what if we just change the representation in the object-centric representation? Then it's like more close to human-like thinking, right? But then we have to learn the object-centric representation. I'm not gonna do very deeply about the object-centric learning, but let me go through briefly. If you're doing computer vision, you might have heard about the object-centric learning. There's a very foundational way called slot attention from Locatello. This is basically encoder-decoder framework, and between this encoder and decoder, you might have the feature space, right? And you bring like a bucket, like a basket, to put each features, and like this basket is for each object. So there's a mechanism called slot attention that puts each feature to each slot. So there's like a binding problem of feature to slot. And they decode with this basket so that the model can have well-aligned information with the slots. You don't have to read this all, but I brought this because this is United Transformer class, and slot attention is about self-attention. So what I want to show is how to bind the features to the slot is you do self-attention, where key is the input features. For example, in the Dyna V2, there's like a patch embeddings, right? You allocate each patch embedding to slots. You're basically assigning them. And the value is also the input features. And you update the slot by using GRU. So you iteratively update the slots, and now the slot will have the object-aligned representation. So this is how usually the models are getting object-centric representation. This is very, very naive approaches. There's so many advanced ways. For example, this is for image, and there's like a video slot attention models as well. So yeah, you can give it a try. And what would model behave if it perfectly understands the dynamics? Let's say the model learned the monkey eating banana. If model is like truly understanding this eating mechanism, the model might be able to infer what is happening to banana when we cover the invisible cloth on banana. So even though you're not seeing the banana, if you see like a monkey like moving their mouth constantly, you can imagine, oh, like a banana might get shorter, you know? And vice versa. If you make the monkey invisible and like a banana is disappearing, you can infer that like a monkey is eating something, right? This is like very core motivation and very core explanation of causal JEPA. This is really relevant of what I'm doing right now. And if you think of the previous example, it doesn't have to be, the predictor doesn't have to be the causal transformer. As far as we are seeing the only history, we're okay to use multiple time-step history. So we're using a bidirectional transformer here. I would like to mention that. And let's see how the model actually implements the monkey and banana mechanism in the transformer. Let's say we have a nicely aligned representation for each object. And we encode these object states to the representation. For example, let's say our lookback history is 4 frames, so you see 4 frames and next frame prediction will happen. But because this is not a causal autoregressive transformer, this is a bidirectional VIT style transformer, we need the placeholder for this future tokens as well. So we use this as a mask token. And now, so our goal is predict this mask token correctly. And for example, each row means the evolution of each object. Now, as I told you before, I want to mask something. Here, blue dots are observable slots, and the yellow one is mask slots. And let's imagine that we have this mask slot here. What should model do? What is the easiest way for model to have a reasonably low loss and just predict the mask token? Maybe just average the previous and the next token, just like doing interpolation. But that is what we want. What we want is like a learn the object interaction. So like the previous example of monkey, I just mask everything. This is a bit aggressive way of masking, but now the model doesn't have shortcut. It needs to infer the other slots to correctly infer the current state or the mask state. But what if we want to mask 2 objects at the same time? This can be happen because in slot attention, you have to fix the maximum number of slots. The number of slots doesn't vary during training. So you kind of give a plenty amount of slot to give a model freedom, okay, what information should define as a slot. And sometimes in the scene, for example, we define 8 slots, but we only have 3 objects in the scene. Then just masking only one object, only one slot might not be enough. And then now we want to put this into transformer. And we have to flatten, so we have to do positional encoding before then. Okay, there's no problem by temporal positional encoding. But when we are trying to do the positional encoding in the slot axis, there's a problem. Because what object-centric models are doing is they do not define the order of the objects, but rather than the object-centric models are permutationally equivalent depends with respect to the object orders. So this is basically not list, but set of objects. And then like if you are masking multiple objects, the model might not know, okay, what to predict, because these slots are not having object identity. So the video slot attentions can keep the temporal consistency inside the video itself. For example, video A kind of have the consistency with the object order, but we cannot guarantee that video A and video V are having the same order of objects. So now what we do is we do not mask the very first time step, in this case, time step T-3, and we use this information as a slot identity. And what we are doing is we define each mask token with the identity token plus learnable mask token with the positional encoding. And this is like less aggressive because you have an initial condition of each object. So it makes more sense when you predict the mask tokens. And the other part I want to talk about is action conditioning. The world model should condition on the action properly. And what the Dyno world model is doing is they concatenate the action embedding behind the patch embedding. For example, Dyno v too small has 384 dimension of the features. And let's say we have 10-dimensional action embedding. And what Dyno world model do is they duplicate it to like the number of the patches, and they just like put the action embedding after the patch representation. So now it's like 894 per patch because we added this action embedding after the patch representation. But this is not really optimal way, I think, because what we want to learn is something like this. Why don't we consider action as another node of the graph? The causal JEPA does not recover any true causal graph, but its motivation is grounded in the causal graph. So for example, because we define each object representation, those are kind of playing a role of the nodes, and we also try to use this action as one of the nodes. So in this current situation, the action is added like something like this, not as a part of the feature representation. So this is the this is the architecture of the causal JEPA. So to sum up, you have the history frames, and you put this into the object-centric encoder to get the object representation. And then you select some amount of objects to mask, and you mask it, and you put this into predictor, which is bidirectional transformer with the action, and then you're predicting every mask tokens. And now we will see some results. I did 3 experiments based on our goal. Our goal is understanding the object dynamics. And first thing is reasoning on the counterfactual questions. And second thing is planning and control. And third is physical implausibility. So in the Clever, we did an experiment with the other existing models as well. But what I want to highlight is the model without masking. What I want to say here is the performance is not because we use the object-centric representation, but the core is masking, like in the banana example. So if you see the CJEPA result, not only average accuracy is better, you can see there's a clear gain in the counterfactual question. This counterfactual question is very well resonated with our original motivation, because the counterfactual is asking something like, oh, what if this object doesn't exist? What if this object exists? Like something like this. So you have to understand like how the object interact each other. And the next example is push T, planning. The agent tried to control the object to reach the goal state. And here I want to emphasize the efficiency. If you can see the Dyno world model baseline, you have 196 patches. If you imagine you are having 224 by 224 images, and each patch should have a 384 dimension of the features. And if you're using object-centric representation, the number of tokens are significantly less than that. And because now we have the clear semantic from each token, the feature doesn't have to be super large. If you think of, there's nothing much to include in the object. For example, texture, color, shape, rotational state, and location. That's not that much. We don't need like a really huge representation space. So after we only putting object-centric representation instead of the patch representation in the Dyno world model, its performance actually drops a lot. And this can be true because Dyno world model used the causal transformer, and we use bidirectional transformer, right? And the object-centric representation, if you think of, doesn't necessarily have to include the velocity or acceleration kind of stuff because you cannot define those properties by only looking at the single static image. So this drops the performance a lot. And after we changed the action conditioning method, treating them as a separated node, and we changed the transformer to the bidirectional transformer, the performance gain is significant. It gains this 15% of absolute percentages. And after masking, compared to the OC object-centric dyno-world model, you gain 28%, which is pretty large. And compared to the OC JEPA, the only difference is object masking. And this object masking actually helps the model to understand this dynamics. And this is the effect of the action conditioning. As I told you before, the latent concatenation in the red line denotes the action conditioning method based on the dyno-world model. But after we treating this action as a separated node, it clearly shows the margin. And there's an additional experiment on fear. Fear is among 3 data sets we have, it's like a most complicated dynamics. And there's a lot of formulation, configuration, and you need to learn precisely what is happening in the scenario. And when I compare the OC JEPA and C JEPA, OC JEPA often generates a physically implausible scene. You see like the bar is floating below the fixed bar, which doesn't make sense. And this can be done by just learning correlation, like when 2 bars are closed, they just stay there. But that's not true, like that's not how physics works. So by the training method of object masking, you keep asking the question to the model, what would happen if this doesn't exist? What should you consider to predict the mask token? It can learn the true dynamics. And this is the attention probing for this previous example. You can see the failure is actually coming from attending to the wrong irrelevant object. So for example, OC JEPA relies on the cup, which contains the blue ball. And the C JEPA conditioned on the right bar to predict its future state. And here the causal JEPA, the terminology causal can it can stand for many things, but here we use the causal as a temporally directed predictive dependencies, which means that because we're predicting the future from the history, the edge is directed. And to predict the mask token, you need to attend to the relevant object, so we call it temporally directed predictive dependencies. This is not the very conventional and traditional way of defining causal, but recent modern causal machine learning is this kind of definition as well. And here, to go back to the role of the object masking, we would say this predictor finds influence neighborhood. Influence neighborhood we just define as name, but it's just a predictively sufficient set. So it's like a minimal set that it needs to predict the mask token correctly. And this can be true, more formally, this can be true with 4 assumptions. The first thing is we do not assume there's an instantaneous relationship. And the second assumption is that every training instances should share the same mechanism. For example, the gravity should not change along videos. There's like a governing rule applied in the whole data set. And the third assumption is object-aligned representation. This is the most tricky in the practical sense, because this assumes that our object-centric representation is constant throughout the video. It should not getting swapped. The object should not be split into the different slots. And our representation should reflect the scenario faithfully. And the fourth is history sufficiency. This is because we use finite history. For example, we see 4 previous frames and predict the next frame. And this 4 history frames should be enough to predict the future. And to make this causal machine learning to practical, we do not assume first-order Markov process, as I told before. The object-centric representation usually does not follow the first-order Markov process, and we allow confounder. The confounder makes things really tricky because we cannot recover the true causal graph usually because of the confounder, but in the object-centric representation in the real world, this is kind of inevitable. So I would like to answer these questions really quickly. What happens if object-centric representation is not faithful? A little bit is fine because, like still masking object slots is still some kind of inductive bias, even though our masking is not like perfect. So a little minor like a wrong model can be okay, but if it's really bad, it doesn't work. Is there any way to recover the true causal graph? No, in our method. There's confounders, so we cannot recover the true causal graph. And also sometimes it is really hard to define what is the true causal graph in many scenarios. How to select the number of objects to mask? This is a good question. Because we have a fixed number of the slots and the number of actual objects are varying depend on which frame are we looking at. The ideal amount is just only one foreground object without the background slots. But we sometimes cannot control this really well. So I would say decide the number of masks based on the data statistics. Just guess your perfect number of the mask, and you should sweep a bit to find the perfect number. And the largest limitation is coming from the object-centric encoder. The object-centric representation does not work really well on the occlusion situation. And, in the middle of the video, some objects can appear and disappear, but this kind of slot attention cannot handle this scenario really well. So this is some pain point of this model. And finally, we got back to this 3 components of LeWorldModel again. In the beginning of the talk, I said there's a 3 component that we should consider to make a good LeWorldModel. And for the good state representation, we use this object representation. And for a good transition model, we did object masking to let model learn the predictive sufficiency. And about the dynamics model, we kind of tweaked the method to condition the action. So we treat these action variables as a separated node. I think this is all of the causal JEPA part, and let me quickly put to Lucas.
So hi everyone, my name is Lucas. I'm a third-year PhD student at Mila, advised by Damien Sieur with research lens at Samsung, but I work closely with Randall Baestrero, with Prof. Brown. And the work I'm gonna talk about today is a work I done in collaboration with Quentin Lelidec, with postdoc at NYU, with Yann LeCun, Damien, Yann LeCun, and Randall. So today what I'm going to talk about briefly is how to make this whole LeWorldModel stuff and JEPA stuff pretty simple to train. And I'm not going to tell you again what is a LeWorldModel. I think Hazel did it pretty well. So I'm going to go directly to what we did. So just before that, I would like to talk about a big problem. So as Hazel say, JEPA aim to learn representation in abstract space. And so it's directly in opposition to generative modeling, where in generative modeling, what we try to do is you try to model your input space. Basically, you try to learn a representation of your input space and try to do stuff in your input space. Sorry. And so JEPA say that this is for most of your tasks not desirable. For instance, if you do self-driving car application, you most likely don't care to model the movement of the leaf of the tree, okay, in the road. You don't care to model that. If you do generative modeling, by definition, you will have to model that because you want to model all the detail of your input. So your loss is going to give signal for that. So what JEPA proposes is to first encode all your inputs into an abstract space, typically with an encoder or a neural net, and then try to model the dynamics of your space in that latent space. Okay. So it's pretty nice when you say like that, but if you look on the right, the image I put, if you just do that, you suffer from what people call collapse. And so what is collapse? It's a failure mode where you can see that if I do nothing, I don't put constraint on the distribution of my embeddings, your model on the right can simply learn to disregard the input and just produce a constant vector. And so you can minimize the prediction loss in the latent space just by saying, okay, I will gonna encode everything as a constant vector like 0. And then it's trivially easy to predict what is gonna be the next state. It's gonna just be 0 again. And so the whole research on JEPA, and like a big part of the research on JEPA is how do you avoid that collapse? So as Hazel said before, I should add Causal JEPA in that previous JEPA recipe as well. You have VJEPA that try to do that try to avoid that collapse with exponential moving average. You have LeWorldModel that use pre-trained encoder basically to avoid the collapse, because if you use a pre-trained encoder and you froze it, you can produce non-trivial embedding, and you can learn the dynamics directly in the embedding. So it's essentially supervised learning, LeWorldModel. And then you have PLDM that try everything end-to-end. So they train the encoder, the predictor, and everything end-to-end. Their action condition model as well. But they use something called VCREG. And what is VCREG? It's just an anti-collapse regularization term that try to make the covariance matrix of your features, of your latent features, identity. So basically you want each dimension to be decorrelated from the other of your feature space. Except for like the covariance metric, the diagonal line is 1 typically, so like you have a positive correlation. The problem with PLDM is, as you can see on the slide, you need to apply one term for the variance, one term for the covariance minimization. You need to do that spatially and temporally, so you have 4 terms. They add an additional inverse dynamics loss to try to gain more information about the action. Whatever, it's 5, plus you have the prediction in the future, the L2 minimization you see on the right. So your predictor try to predict the future in the latent space, and you compare that with what your encoder say about the future should be. Okay, and so it gives you a 6-term loss. So it's pretty difficult to tune that because you have 6 hyperparameters to tune, and that's why we propose LeWorldModel. So what is LeWorldModel? It's just a simple JEPA that doesn't use any tricks. So there is no exponential moving average, no masking, no stop gradient, no pre-trained encoder, and also no unstable loss. Why? Because we have a single hyperparameter, and we make the model such that it's only 15 million parameters. So it means you can train that on a single GPU. It's fully end-to-end from raw pixels, so there is no auxiliary information such as proprioception information or whatever. And we observe that it's 50 times faster than LeWorldModel for doing planning. So basically, what is LeWorldModel? It's basically JEPA in its pure essence. So what you do is you take an observation OT plus 1, so the next observation. You process, you process both of them through a shared encoder, and you get a representation ZT and ZT plus 1. What you're gonna do, the task is you will use ZT and the action at step T and try to learn a predictor to model the dynamics. So you're going to try to predict the future. So you have an estimation of the future called ZT+1, and you compare that to what your encoder predict for the next state. You use mean square error, and you use what we call SIGREG to avoid collapse. What is nice is that basically what I told you about before with JEPA is literally what you see, and the code is exactly what I just described. So if you look at the pseudocode on the right, it's actually not that much a pseudocode, it's literally the true code. You encode, you predict, you compute your prediction, your future prediction error, and you use SIGREG to avoid collapse, okay? So you can see that at the bottom line, at the return, I have a single hyperparameter lambda. So this is the only stuff you need to tune. And because you have a single hyperparameter, you can do a bisection. So it's log n to find the optimal lambda. So it's pretty nice because you can really easily tune the model. And so what is SIGREG now? So this is the stuff that avoids your representation collapse and makes sure that your ZT are informative about what is inside your observation. So basically, you can see ZT as a learn abstraction of the world or a learn state. You have an observation of the world, which is the image OT, and you try to learn. You try to estimate the state, the ground truth state. Okay. And so, how do you prevent collapse? Basically, we use a simple regularization called SIGREG for sketch isotropic Gaussian regularizer that Randall and Jan LeCun introduced last November, I think, if I'm correct. And the idea is very simple. The math are a bit tricky, but I invite you to read the paper. It's a very nice paper. But the idea is very simple. You take the distribution of your embedding, okay? So you take your batch, you look at how are your embedding ZT distributed, okay? And you will try to optimize that distribution to be isotropic Gaussian. So how do you do that? You could use generative modeling to do that with the KL divergence and everything, such as in variational autoencoder. We don't want that here. We don't want to use generative models. So what you do is you're going to try to use a statistical test. Okay, so in statistics, you have tests that tells you, given an empirical distribution, how close is it to Gaussian distribution, okay? The problem is that our embedding space is very high dimensional. And so there is no test that, like basically the statistical tests, they suffer from the curse of dimensionality. So it's pretty difficult to directly use a test to optimize in high dimensional distribution. And so what Randall had for idea is to basically project, you sample a lot of random direction in your latent space, and you're going to project all your embedding into one dimension. So as you can see, for instance, if you look at the red arrow on this image, and you look on the right, you can see that once you project your embedding into that direction, you get a unimodal, a univariate empirical distribution. And now you can optimize, because it's just a 1D distribution, you can optimize to make that Gaussian. And if you do that in a lot of direction, there is a theorem called Kramer-Wald theorem that say that if you optimize the marginals to be Gaussian, then the joint is going to be Gaussian. So basically, if you do that for a lot of random direction, you can prove that your latent embedding distribution is going to be Gaussian as well. So it makes us sure that we will have informative embedding. So that's pretty nice. Okay, so now how can let's imagine you train your world model, blah, 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 blah. How can you make sure that you learn a good world model? So there is two ways. I know two ways. If you know more, then that's nice. We can talk about that. But the first way is online control. So can you use your learn world model that is action condition? And can you, in an online way, optimize this action to perform control? So this is the first thing. And the second thing we are going to talk about after is try to assess if your world model understands intuitive physics. But let's focus on control for now. So how we perform control is basically we are going to freeze your world model, okay, the learn world model. You're going to sample random trajectories of action. and you're gonna optimize by rolling out the future. You will optimize that sequence of action to match a target goal. So for instance, let's say you have a goal frame, OG, okay? You start from the current frame O1, you both encode them through your encoder, you got the initial state, latent state Z1, you have your target state, which is ZG, okay? And then you sample an initial sequence of action, and you use that, the first one, with your first state inside the predictor, it gives you Z2, then you use the second one, etc., blah, 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 blah. And after each step, you compare how far are you in your latent space to the representation of the goal. Okay, it can be MSE, for instance. You use the MSE loss to estimate how far you are from your goal. And because your predictor is differentiable, you can, for instance, backpropagate until the action, try to sequence of action to minimize the distance with your goal. Okay, so I can show you some results. You can see that we consider 4 tasks. So the first one on the left is called 2 room. It's a simple 2D navigation task where you need to move from one side of a room into the other by passing through a door. Okay. Then you have Reacher. It comes from DeepMind control suite where you need to, you can see on the right, you have a 2D, a 2-joint arm, and you need to match a target location from a given goal, okay? Then you have push T. So push T, Hazel already present, but the goal of push T is to push basically the T to the green area. That's as simple as that. And you can only push, you cannot pull. And OG Bench Cube, it's a 3D environment where the objective of that environment is to make the cube, your cube, it's a 3D manipulation robotic arm where you need to make the cube matching a target location as well. And so I think the most interesting result is, the first one is push T, because you can see that NeuRalModel, okay, has been trained with proprioception. And you can see that LeWorldModel without proprioception beat NeuRalModel with proprioception with half the parameter. But what is most interesting is if you remove the proprioception of NeuRalModel, you see that the performance drop. Okay, and LeWorldModel, because it doesn't have proprioception, it beats like by a lot NeuRalModel without proprioception. And PLDM, which is the only other one that doesn't use proprioception and that is fully trained end-to-end, also have very bad performance or push T. So it was very nice to see this result. So for Richer, we beat PLDM and NeuRalModel as well. But what is really interesting is that for OG Bench Cube, for instance, we beat PLDM, but we don't beat NeuRalModel. And the most likely explanation for that is that we only train on trajectories coming from the dataset, but NeuRalModel has been pre-trained, because it's a pre-trained encoder, it has been pre-trained on 124 million natural images. And consequently, it has a better understanding about object and 3D than we have, because it has been trained on a lot more data. And also, very funnily, you can see that for 2 room, even if it's the simplest task, almost all the baseline destroy the task, but for us, we don't. And this is actually a limitation of Segreg that exists for now, is that if your intrinsic dimensionality, so what I mean by that is the true dimensionality that you need to solve the problem. For instance, for 2 room, it's just 2, because you just need to know the X and Y of the agent. As soon as you know that, and I give you a target location, you can solve the environment. If that is very much smaller than the embedding you use, there is no way that you can produce Gaussian embeddings. At least your Segreg, when you optimize, is gonna need to create fake stuff to be able to be Gaussian. Like to use some information to make your latent space Gaussian. So it doesn't help you, basically. There is research going on to try to fix that, and actually, we know that if you carefully tune the hyperparameter, you can somewhat overcome this issue. But for the sake of fairness, we didn't hyper-tune all the hyperparameters, and we keep the same hyperparameter across all the environment. But the most interesting part, why it's very nice, is when you look at the planning time. So for DynoWorldModel, and we heavily optimize DynoWorldModel to try to be as fast as possible. The fastest we could go for doing the full planning, okay, is 47 seconds. And the reason for that is because your predictor takes all the patches, and you need to predict all the patches. So it's quite slow because of the quadratic cost of the attention to predict the future, right? As for us, with LeWorldModel, we have a single embedding for representing the latent state, because we just use the CLS token of the encoder, and it allows us this plus some other tricks. We didn't optimize a lot for that. We could go a lot less than this, but we can go to a full planning time under the second, which is very nice. Like it's like almost 50 times faster. Another thing interesting is that if you fix the flop, okay, so if you fix the flop that you use for planning, and we fix the flop at those of LeWorldModel. So if you reduce the planning time by tweaking the hyperparameter for the planning until DynoWorldModel plan under a second, you can see that the success rate drop by a lot for PushT and for OGBench Cube, which is expected, but it showed that at similar budgets, we outperform even on OGBench Cube DynoWorldModel. So that's for the control. For intuitive physics understanding, we did something pretty easy. Sorry. The first thing is we probe the latent space. So we just took the encoder from LeWorldModel and we froze it, and we trained a linear or an MLP probe, nonlinear probe, to try to predict the coefficients of the simulation for that state. Okay. So I will not go that much into the detail. You can have a look at the paper for that. But what is pretty interesting is that, for instance, for OGBench Cube, you can see that the linear probe with LeWorldModel, we almost all the time have a lower mean square error, which means that like if you compare with the MLP probe on the right, it's almost DynoWorldModel all the time that have the lowest mean square error. And so what it suggests is that our latent space is less entangled than the one of DynoWorldModel. So it's more easy to recover the coefficient directly from the latent space rather than DynoWorldModel. And it does make sense, I think, because as we use Sigreg, it push like the latent space in such a way where your each dimension are somewhat meaningless. So it's not fully disentangled, but it's somewhat more than DynoWorldModel, which is pretty nice. Another thing that you could do, which is pretty cool, is to try to see what happens when you violate the world model. So if a sudden change in the dynamics happen, does your world model predict that this is a violation? And so what we did for that is, as you can see on the left, sorry, the cube color and cube teleportation are inverted. But if you look on the left, you can see that we have a normal trajectory where your robotic arm pick up the cube and move it to the right, for instance, okay? Nothing happened. And then we consider two perturbations. For instance, we change the color of the cube. So this is the one on the right, not in the middle, suddenly at a given frame, okay? And another transformation we did is randomly, like suddenly, this is the one in the middle, the cube teleport, okay? And so if you look on the right, you can see that the x-axis are the time steps, okay? And the y-axis is the prediction error. So this is the difference between what your predictor, okay, predict is gonna happen and what the actual embedding of the next state look like, okay? And so what you can see is that if you don't have any perturbation, so this is the gray line, it's fine. If you change the cube color, it's a bit higher, but it's very negligible. So it means that basically your world model don't care much about the color of the cube, which is pretty cool because you don't need that for the dynamics, right? You don't care about the color of the cube. But if suddenly the cube teleport, then the prediction error shoot a lot, meaning that your world model didn't predict that. Some people say to me often that, yeah, but it's just out of distribution. And I would say it's true, but I think it's not very meaningful to say that because as human, like when you violate your own model, it's also very out of distribution. That's why, for instance, when someone do to you a magic trick where they make a coin disappear in front of you, you're suddenly very surprised and like it frustrates you a bit, you know. It's the same here. It's because the prediction error is very high. So we did two other small experiments as well. The first one is we try to embed the location of the agent and the T, and we try to make the agent location and the T location move. So you can see that the middle plot shows you what happened, like the different location, and we try to project with a t-SNE plot the embedding space to try to see if we can recover this exact relative distance between all the different locations of the original space. And what you can see is that up to permutation of the axis and rotation reflection, this is exactly what happened. So we recover basically the relative distance in the original space, which is pretty nice. The last thing we did is we froze the world model and we train a decoder to try to interpret what is happening when you make future prediction. And so for that, you can see that we give a context to a world model. So this is the first reframe of the top row you see, or the bottom, the second row. Okay, so we give that to our model. The first row is really what happened in the future. On the right, where you have open loop prediction. So this is actually what happened in the trajectory. And then on the second row, you have what your world model imagine when you give the same sequence of action that has been taken for the original sequence. And you can see that the world model predicts somewhat the reality when you give the sequence of action. But what is very interesting is that if you look at the second rollout with the cube, okay, so you can see that we predict very well what is going to happen with the cube. But if you're very careful, you can see that at frame 15 and 20, the angle of the gripper is opposite. And so basically, you can see that the world model didn't learn the rotation of the gripper, which was pretty interesting because it still was able to solve somewhat the environment. So there is many limitations for our model, or as I like to call them, research opportunities. So for now, you are doomed to short-term planning horizon. So if you can unlock that, that would be very nice. Another problem is that you reason at a single temporal level. So we need hierarchies, basically. You need, for instance, when you think about, oh, I need to go to the airport, you think at a different hierarchy, right? The airport is your goal. You think, okay, I need to go to my car, then I need to go to airport and blah, blah, blah. And then only at the end, it translates into muscle movement, right? So you don't all the time think in terms of muscle movement. So we need that as well to be able to predict further in the future. A very important stuff as well is to move from this toy environment. Like I fairly agree with this kind of criticism that it's very toyish experiments. And so can we move to real world robotics? Or very stochastic and partially observable environment like Minecraft, that would be very nice. And also a big problem, I think, is how do you specify your goal? So for now, you can see, as I explained before, you need to provide a visual goal, but you don't all the time have access to that. And it doesn't tell you anything about how you should solve the task. So for instance, if you have a plane that needs to land, okay, you don't want to just show a picture of the plane landed to do the planning. You want to specify how smooth should be the landing and everything. So we don't know how to do that for now with this kind of approach. I would like also to take just 2 minutes to do a bit of advertisement for something we have been pushing with a lot of Randall students and a lot of people for the past few months, which is called Stable World Model. And if you're interested about world model research and this kind of stuff, you should definitely have a look for that. So it's a GitHub library, fully open source that allows you to train very easily world model. So you have all the baseline I discuss about and Hazel discuss about that are implemented there and heavily tested. You have all solver to do planning. You have many environments. We recently added mind control and Minecraft, and we are in discussion to add support for real robot data also very soon. And everything is very heavily tested, and there is documentation. So yeah, feel free to give a try and give feedback or contribute to the library. That would be very cool. Thank you.
Okay, great. Thank you so much. Let's give a round of applause to our speakers today. So now we'll be soliciting some questions. We have some online on the Slido, but I'll also be looking for in-person questions in case anybody here wants to ask anything as well. So we'll kind of balance between both, and I'll let you guys figure out like who should answer each question, or if you both have insights for anything, that's also great. Yeah, does anybody here have any questions?
Background. I'm just curious, how does the role models will transfer to physical AI space? Like, how can we see them moving forward in robotic space?
I would give it to Lucas, probably. Lucas, can you hear us?
Yes, yes. Can you repeat the question, please?
Oh, so how can we expect the role models to be in the physical AI space? Because we already have a diffusion-based foundation models like Groot or maybe Pi and also Size Zero. Like, using role models, can we expect some more applications in the robotic space?
Okay. So first of all, I will be very skeptical that the current VLA model have a good understanding of the world. Like, there is no reason for that. Okay, they are not trained to predict the consequence of their action. Okay, and I will be very skeptical to see something that doesn't know what is the outcome of his action be very reliable to do physical AI. So as human, why you are very good at what you do is because you can predict what is the consequence of your action in the real world, and that's what our model try to do. VLA, they don't do that. So if you want to have physical AI, basically you need our model. You cannot bypass that. I think as Jan say often, like VLA and everything, they can be very helpful for simple stuff where you don't need to predict what is going to be the outcome of your action in the real world. For instance, like if you want to make robots that, I don't know, do some dance or whatever, they only need to know their internal dynamics, okay? They don't need to know how to interact with the real world. To interact with the real world, you need to predict the outcome of your action. So you need role models. I hope that answers your question. If not, happy to clarify.
Sure. Thank you.
I would like to answer one more sentence. I think Professor Sherry Young in NYU, she has an opinion that our model can be an evaluator for policies. So I think this can be also your answer. Yeah.
We have someone's Slido. Let me see. Someone's asking, masking is shown to improve predictions, but is it really necessary to learn the world model? Does it mean that prediction loss alone is insufficient?
The prediction loss, okay, let me assume that you're still talking about the object-centric representation. If you only do the prediction loss with the object-centric representation, the shortcut or the what model will learn it can be the self-dynamics. We cannot guarantee that model learns the interaction-based dynamics. So I won't say that is insufficient, but with the masking, I think you can reinforce the model to learn the object dynamics.
Yeah, that makes sense. Someone's asking, do you have any insights on how JEPA learns to plan ahead beyond just the next frame?
So for the, is it all of the question?
Yeah.
Okay. We strictly follow the evaluation method, the planning of the DynoWorld model. So with the predicted future frame, we do it auto-regressively to reach the long horizon planning. And we use the parameters for planning as well.
Any in-person questions? Okay, I'll continue with the online ones because we have quite a lot. Let me see. Someone's asking, what would a JEPA native agent architecture look like compared to current LLM-based agents?
Lucas, do you want to answer?
Of course, can you just repeat the question? It's pretty difficult to hear.
Yeah. Someone asked, what would a JEPA native agent architecture look like compared to current LLM-based agents?
Okay. Basically, the way it differs is that you learn action condition model, right? So LLM agents, you don't learn action condition model. As far as I know, I'm not expert in LLM as well. but you learn to use tooling and to make tool calls. This is not what you do when you do world models. What you do is you learn, okay, I have an action, I am a current state, what is going to happen in the future if I take that action, okay? This is not how you train LLMs, so this is one step that differs. And the second thing is that by construction, okay, you can just learn to model the future with with world models, and then use planning by using old concept of control theory, such as model predictive control or whatever, to directly convert that into an agent. You don't need post-training or whatever. You can do that zero shot. So that's pretty neat. For LLM, I'm not sure, so I cannot reply for that.
I think that makes sense. Yeah. I guess this is kind of. Let me see. Yeah, do you think JEPA models are less prone to hallucination than transformer-based models, since they hopefully learn a more accurate representation of the world? Not sure if you guys might have any insights.
I can answer first, and Lucas, you can just add your opinion on it. I'm not sure what kind of hallucination the person asked, but in the predictive sense, because JEPA model is, as I mentioned in the earlier part of the talk, the JEPA is energy-based model. So rather than just predicting the full pixel space, what it evaluate is, is our predicted future make sense? Like, is it possible situation, or like is it impossible? So I think in that sense, in the sense of the representation will be more suitable for world model, I think. Yeah.
Yeah, so I can complete on that. So I think the original question was to compare JEPA and transformer-based model. So I would like just to emphasize that JEPA is not an architecture, a new architecture. Like, for instance, for LeWorldModel, autoencoder and predictor are two transformers. So JEPA is really a framework to try to learn world model. It's not a new architecture, okay? And second, I think you can have definitely an hallucination if you don't learn a good model, okay? But this is not at all the same hallucination as you have with LLM. Because LLM, they have multiple sources from hallucination. One of them is that they are not grounded in the real world, okay? With world model, you can easily fix that. Additionally, also, you can say that with world model, you can have another source of hallucination as well, is that when you optimize the action sequence that you want to do for doing planning, you could have actions that are not meaningful for the real world. For instance, let's say that your action is between -1 and 1, but your optimizer say, okay, you should use -2 as an action. So you can have this kind of hallucination. Otherwise, it's just about the quality of your learned model, and this is just a matter of data and capacity. Hopefully that makes sense.
Yeah, no, great. I think that makes a lot of sense. Thanks. We have someone asking, are world models better than the diffusion-based models for robot control?
I think we would have similar answer as the previous one. The world model can still use the diffusion model.
Yeah, of course. You could use diffusion model to train JEPA. Actually, some people try to do that. Diffusion model have some advantage and some limitation as well. So yeah.
Any in-person questions? All right, we got one at the back.
Kind of a longer horizon question, but you mentioned that you might consider planning through this whole family of different algorithms developed for control, like model predictive control, etc. And you mentioned that it might be possible to use these things as kind of a grounding signal to train policies. Do you think that it's kind of a combining those approaches? Maybe that's what you already meant by training policies, though, of turning up a lot of compute on something like an model predictive controller for a relatively long horizon, and then distilling those back down into policies might be an efficient way at getting some longer horizon behavior for one of those problems and/or research directions you mentioned.
You want to go for it, Hazel, or?
You can go ahead.
Okay. Yeah, you can definitely train a policy on that, because as soon as you have our model, basically you can do either two things. You can use that directly and optimize your action sequence to have a zero-shot policy. Or you can do same as Dreamer, for instance, and use your pre-trained world model and train reinforcement learning policy on that, and periodically go in your environment and collect better data, fine-tune your world model, improve your policy, and blah blah blah. You can do that as well. So in the future, I think you will have something similar to System 1, System 2, same as human does, where you will have a condensed, like basically an action-reaction policy, where you will learn to directly predict what is the action I should take to have that goal given this state, okay? And then for difficult tasks that you are not very confident about, planning and model predictive control to have more careful plan and situation. For instance, when you want to learn to drive a car, maybe at the first 20 hours, you will use model predictive control to make sure you don't kill someone. And then after 20 hours, you think you're an expert. So you can basically distill your prediction of model predictive control and planning to a direct policy that outputs directly the action.
Right, great. Unfortunately, that's all the time we have. Hazel will be staying after in case anybody has any questions or wants to talk to her. So thanks again to our speakers for the very insightful talk. Thank you.